Hi there, and welcome back to Basic Math for Economics. In this video, we're moving on from unconstrained optimization to actually talk about constrained optimization. So let's take a look at this, and before we actually can get into constrained optimization, we need to actually talk about constraints. So anyways, the idea of a constraints comes from the fact that we all like nice things, but often we can't get everything that we want. So as an example of this, if I gave a utility function and I told them they could maximize their utility with no restrictions, someone might come back and just say they want an infinite amount of everything. You know, if they had two goods, they just say, I'll take all of the X and all of Y, you know, take everything. But in the real world, that can't happen because we're limited. And we're going to find that with almost every kind of utility maximization problem we deal with, we're going to have a constraint, or basically a limitation on what we can choose. In this case, it would be a budget constraint. We're limited by how much we can spend on these goods or services. So when we're doing optimization problems, we need to incorporate those constraints in, and we need to make sure that they're working with what we've set up before. So the problem also when dealing with constraints is that there's no guarantee they're actually going to bind. So let's take a look at a budget constraint, for example. So if the constraint binds in a budget constraint, it means that we expend exactly as much money as we have, or as that we can allot between those two goods or services. But we may have a special situation where we have what we would call a bliss point, where our consumption level is maximized below our budget line. Basically, we don't want to spend all of our money. We want to stop at some point. So we need to know when we are maximizing whether or not that constraint actually binds. We need to be able to test for that as well. So the good news is we can use some mathematical techniques and we can figure out whether or not a constraint will actually bind. So here's an example of what I'm talking about. Let's suppose we had a budget line right here. A binding constraint, we would find that our equilibrium bundle of x star and y star was going to lie somewhere along the line itself. It'll be a point on that line. But if we had a bliss point, we could find our equilibrium is going to be right here underneath the line where we don't spend all of our money. So anyways, in order to figure out how we're going to work with this problem, we need to work with our budget constraint. Again, this is a utility maximization problem. And all this budget constraint says is it's px times x, which is the price of x times x. That's how much we spend on good x, plus the price of py times y, where py is the price of good y, has to be less than or equal to I, which is our income. So how much we spend on x plus how much we spend on y must be less than or equal to how much money we have available to spend on those two goods. So if we're going to use this constraint in our problem, we actually need to rearrange it. And again, we don't know if this constraint's going to bind. It's going to depend on the structure of the utility function and how restrictive the constraint is. So in order to figure that out, we rearrange this constraint. We do a little bit of algebra to it. And we set it so that it is greater than or equal to 0. So I can achieve that by subtracting pxx and pyy from both sides. And I get this constraint right here. I get I minus pxx minus pyy is greater than or equal to 0. And that's the form that we want our constraint to be in. That's how we're going to be able to incorporate it into our problems. It always wants to be greater than or equal to 0. So the next thing we need to do to put this into our optimization problem is we need to make use of what we call a Lagrangian. And a Lagrangian is a special kind of optimization problem. Basically, we're going to take our objective function and we're going to add in each of the constraints that we have, and we're going to multiply those constraints by what's known as a Lagrange multiplier. So I'm just going to show you how to do this one. So basically, if I had a utility maximization problem for goods x and y, it's going to look like this right here, where we're going to maximize, and now we have three choice variables. We not only have x and y from the original objective function, but we have lambda as well. And lambda is our Lagrange multiplier for our budget constraint. So we maximize our utility function, which is just u of x, y right there, plus our Lagrange multiplier lambda times that constraint. And notice I left off that greater than or equal to 0 part. I just have I minus pxx minus pyy. And this is how we set up a proper Lagrangian right here. It's going to be the objective function plus each constraint multiplied by a Lagrange multiplier. So if we had multiple constraints, which is again possible, we would need to have a Lagrange multiplier for each of those constraints. So anyways, the equilibrium value of lambda is critical in telling us the role of the constraint in our optimization problem. Specifically, it's the sign of lambda. So basically, the higher that lambda is, the higher the number, and whether it's positive or negative, it tells us how much more the objective function is being restrained by the constraint. So basically, if lambda is positive, or lambda star is positive, it means that our constraint is binding and that it is pulling in our objective function towards the constraint. So we know that in those situations, we're going to optimize by being exactly on that constraint. But if lambda is less than or equal to 0, the constraint doesn't bind at all, and we can actually delete it and treat this as if it were an unconstrained optimization problem. And that's also very nice to know. So if lambda is actually equal to 0, we optimize naturally right along that constraint, and we can actually still delete it. It doesn't matter. We would get the same solution either way. But if lambda is less than 0, that's actually a very big problem for our optimization problem, because it tells us that the constraint's actually pulling our solution away from its natural equilibrium, and we don't want that to happen. So it's very important that we check the value of lambda before we say that we're done. We need to make sure that lambda comes out positive. So we'll take a look at that going forward. But otherwise, after we figure out this constraint, our new Lagrangian, we're going to calculate our equilibrium values from our optimization problem the exact same way as before. We're going to use first order conditions. We just have an extra one now. And we're going to take a look at that in the next lesson. But we don't do anything different. We just have an extra equation now that we use. So this whole thing is a simplified explanation of what we call Kuhn-Tucker conditions. Now, again, I left out a lot of the more finer details of this methodology, but it's very powerful, and I use these quite a bit whenever I get stuck in a problem. So I would recommend it's worth going through and learning some of the more finer details of this technique. So if you get a chance, make sure you check it out. Make sure you come to understand it, because it can help you get through any kind of a constraint optimization problem. So anyways, that's actually all for this video, and thanks for watching.